Okay, welcome to the Astronomy Club of Akron's May membership meeting. I'm very happy to introduce our guest speaker, John Crilly. He's a longtime member of the Astronomy Club of Akron, and he's helped us out tremendously, given a lot of presentations, helped us out on telescope seminars, helped us out secure our 16-inch telescope, really instrumental in the installation of that telescope. And John's been out on a lot of cruises over the last 20 years talking to people on the cruises about stars and astronomy, and today he's going to give us one of his presentations that he does on his cruises. Let's have a hand for John.
Well, thank you all very, very much. I think a room this size, I think with a room this size, we shouldn't need any sound equipment. I'm just going to assume everybody can hear me okay? Perfect. We'll go from there. Usually start this one with everything is a UFO if you're bad enough at identifying stuff. And a chart on how to identify stuff. Is it really big? Yes or no? Yes is always on the left. No is always on the right. If it's really big and your retinas are burning, it's the sun. And if they're not, then it's the moon. If it isn't really big, is it moving? Yes or no? If it's moving so quickly you almost missed it, yes. Extra super bright, yes. Ending with a dramatic explosion, bolide or fireball. No explosion, meteor. If it wasn't that fast, is it blinking? Yes, aircraft. If it isn't blinking, are any astronauts waving at you? If so, it's a space station. If not, it's an artificial satellite. Is it twinkling? Yes, it's a star. Is it kind of fuzzy with a tail? It's a comet. No tail? Is it attached to a boat? Yes, masthead light. If not, it's a planet. So with this, these are some planning tools you can use when you're trying to do your observations. These are ancient pictures for my history. As Ron said, I've been giving this particular talk for decades now. I occasionally refresh some of the images, but the science really hasn't changed. And we're talking about what the amateur astronomers look at. This slide is way too detailed and way too much information, but it does give one piece of information that we all should have. And that is, galaxies are not symmetrical in 3 dimensions, they're only symmetrical in 2. They're shaped like a discus or a frisbee or a dinner plate. As you can see, they're quite wide, but if you look at it edge on, it's very, very flat with a bulge in the middle. And dimensionally, it is our galaxy is 100,000 light years across, it's a long way, but only 5,000 light years thick at the bulge. Very, very asymmetrical. And this is what happens when a galaxy is out there and we're looking at it. It can be oriented anyhow relative to us. It might be oriented face on and we see the whole structure. It might be oriented edge on and we only see just the profile like that. All the galaxies that we look at are going to be shaped like this. They're going to have spiral arms. Some will have, they're called barred galaxies. The spiral arms won't take off from the center, but from an offset point. Our galaxy is shaped like that.
You know what causes the spiral arms?
It has to do with
Gravity and stuff?
how they're formed, yeah. Everything started as huge masses of hydrogen, well, huge volumes of hydrogen atoms scattered through space. They began to attract each other. Mass attracts mass. And as they coalesced, they formed, it became a whirlpool. They spiraled in toward the center mass. That's why our solar system and all star systems are shaped like they are. The hydrogen, the lightest element in the center in the star, and then the heavier elements farther out forming into planets, but all showing the same discus, the same frisbee kind of shape. So as the hydrogen atoms accumulated, they spiraled in toward the center, And it got lumpy, and some of the lumps turned into stars, and you wind up with billions of stars in a galaxy, distributed sort of like that. We're somewhere around here, I think.
That's our galaxy?
Yeah, this is obviously not a picture, but an artist's rendering based on the locations and dimensions that we know from all the various studies we've done. This is what a picture would look like.
Quick question, just the basis of one we see in the telescope, what shape is the Andromeda galaxy?
About maybe 30, 40 degrees.
Okay, but it is spiral?
Oh yeah.
Okay, just so.
You can start off by assuming that every galaxy is a spiral galaxy. You'll find that there are some that are not, but we can usually explain that by saying that they were, and then they got disturbed by interaction with other mass. Sometimes galaxies intermesh, and essentially destroy each other. So you get.
What is it?
I'm sorry?
What is all this? Is this one galaxy?
Yeah, this is it. This is just our galaxy. This is the Milky Way.
Oh, the whole thing?
Yeah. Give myself a So yeah, when you see a galaxy, it might be face on like, edge on like this, might be face on like this, it might be anywhere in between. So if a galaxy looks like an oval, as the Andromeda galaxy does, we know we're seeing it at some offset, somewhere between these two orientations. And there's a whole list of stuff that we look at, which you guys already know. We're gonna hit them all as we go. I'm not gonna make you sit there and read the chart. And I'm certainly not gonna read the list to you because in the course of my life, I've spent way too many hours sitting in a room having somebody read slides to me. I have no patience for that, and I presume you don't either, so we're not doing it. We'll start with the solar system objects. Obviously, sun, moon, planets, asteroids, comets. We can look at our sun. We can look at it in a white light. This is what happens when we just use an attenuation filter. We're blocking 99.99% of the light from the sun, but we're not doing anything to it. We're not filtering it. We're just attenuating it. This is what the sun would look like if we could look at it safely. We can see sunspots. We can see active regions around the sunspots. Sunspots, interestingly, always appear in pairs. A sunspot is either the entrance to or the exit from a magnetic tunnel down into the photosphere. The photosphere is the outermost layer. You can't always see them because you don't see them in pairs because the other one might be around the other side, might be around the limb, but they always form in pairs.
Those sunspots,
No, these are sunspots.
that's what caused the northern lights we had recently.
I'm sorry, I'm not hearing well.
Is that what's causing the northern lights we had recently?
Northern Lights?
That's coronal mass ejections. There's some correlation between the flares, the matter that leaves the sun, and the number or frequency of sunspots, but the sunspots themselves don't do it. The sunspot actually, you see in this image they appear black.
Yeah.
That's because they're relatively cool. They're extremely, extremely hot. But compared to the photosphere, which is way, way, way hotter, they seem cool. So they're not real energetic events. It's just a cooling thing.
There's an article in today's paper about solar flares, and there's a cycle in the sun of like 11 years of flares, and it's coming up now soon.
Well, there's an 11-year cycle of sunspots.
Oh,
And we're coming up on the peak.
yeah. That's what-
Sunspots are fairly active now. 5 years from now, if you look at the sun in white light, it will be very unusual to see a sunspot. Today, if you look at it, you'll usually see some sunspots because we're approaching the peak of the cycle. There's no direct relationship between that and flares, but flares tend to happen more when there's more sunspots. And I hope some of you were lucky enough to see the aurora last week or the week before.
Oh, yeah.
Didn't know about it.
See, I missed it.
Wow.
I miss everything.
Well, they still have the photos.
Oh, we were out there.
Yeah, the people that put the photos up still have them.
Yeah, it was really good Friday night, but Friday night I was too lazy to go anywhere, and I live in the city. I didn't get around to traveling looking for a good site until Sunday night when it didn't happen. So I missed it. It has to do with, I've been an astronomer in Ohio for 25 years, and I've just learned never to really get excited about any event that's going to require clear skies on a given day. So I just don't tend to respond to them. I surely wish that I'd gone somewhere Friday night. Would have loved to have experienced them from here. I have experienced them from Michigan,
Yay!
but not from here.
I have a question. I don't know if you want us to wait to the end, but why is everything round?
Okay, I'm gonna make a shot. Why is everything round was the question, if anybody didn't hear that. I'll take a real quick shot at it, and then yes, it is a lot easier for me if we wait till the end for questions.
Okay, sorry.
Oh, no. I'm here for you. Everything is round because everything started off as not very rigid materials. We know that solid objects like planets and stars formed because of these accumulations of matter that was attracted to itself and to other similar elements, and they would combine naturally into a ball. You know, if they had a shape of their own, they would have maintained it, but they had no shape. They were just particles. So as particles coalesce, they're going to coalesce into a, well, usually into an oblate spheroid, but let's say round, because they're mostly round. Once they start, well, of course they're going to be rotating right away because there's rotational inertia as they spiral in toward the center. And because they're rotating, they will tend to be oblate. They'll be bigger at the equator because that's where it's rotating, it's moving the fastest, and it tends to get spread out by the rotational energy. So Earth's an oblate spheroid. Jupiter is an extremely oblate spheroid. The Sun is hardly at all oblate. It's round, call it. But yeah, everything's round because that's everything formed from mass coming together into a ball.
Okay. Thank you.
Well, sure. Okay, now that was the photosphere. That's the outer layer of the Sun. Directly inside of it is the coronosphere. I'm sorry, the chromosphere. This is where all the interesting stuff happens, but you can't see it because the outer layer, the photosphere, is so very, very bright. If we use a very, very narrow band filter tuned to only the light that can be seen within the chromosphere, which is the hydrogen alpha line, which is red, we can ignore most of what's going on in the photosphere and see down in. And when we see down in, we see the sunspots again, but we see a lot more about the outer regions, the energy regions around them. We see prominences around the limb. We call it the limb, it's the edge. And of course they aren't only at the edge, they're also on the side towards us. They just don't look like that because they don't stick out. That's a prominence. But we call it a filament when it's not on the limb. There's a prominence or filament, actually. There's a filament. Filament. Sun, this again was taken during a reasonably active period. Be aware though, that that's why we have sunspots on it. However, these other things do not follow the 11-year sunspot cycle. There are always prominences. You will never look at the Sun in narrowband and not see prominences. Sunspot peak, sunspot dip, doesn't matter. They're always there. You'll always see filaments. That's one reason it's so much more interesting to view the Sun in ultra narrow band, because there aren't any days when there's nothing to see. Also, unlike everything else amateur astronomers look at, it's a dynamic process. You can see it change. If you stared at that prominence for 10 minutes, you would see it change shape and size. Everything else we look at is static. It changes over hundreds or thousands or millions of years. But the sun, it is dynamic. We can see it happening. A little better shot at the prominences. What the prominences are is, it's matter being ejected from the surface, but curving back and re-entering the sun. If it kept going, it would be a flare. And if you get a hot enough flare, and if it happens to be pointed at us, that's when we talk about the radio interference from flares. It's when we talk about the aurora from flares. But there usually aren't flares, because usually what leaves just rotates right back down. Another little more detailed shot of some filaments. These would be prominences if they were pointed the right way. And again, the active region around the sunspots. The sun is rewarding to look at in narrowband, it's just that it's pricey. And you can look at an eclipse. That's one object that I did actually manage to catch that relied on the skies on a given day. But as you can see, I didn't have clear skies. I was shooting through clouds. That's why the light's so scattered and diffuse, and why it doesn't look like the images that people took when they had clear skies. Nonetheless, it's the best I've ever done, so there it is. That's a total eclipse. We can look at the moon. The moon's a relatively high contrast item. It doesn't move very fast, and it's large, half a degree of sky. So we look at, am I blocking people's view of the screen?
No.
Thank you. But it's relatively high contrast, very easy to shoot. If you want more of a challenge, well, here's another one where you have to wait and hope that you have clear skies on the day. And it does happen reasonably often. Lunar eclipse, once a year, they're not infrequent. They always look the same. The moon gets dimmer and browner. Why is it brown? We know the moon's actually gray. And why is it just dark? Why is there any light at all hitting it? That's because a lunar eclipse happens when the Earth gets in the way and the moon moves into the Earth's shadow, so the sun doesn't shine directly on it. However, the Earth has this pesky atmosphere. And when the Earth blocks the sun at the edges of the Earth, you've got this atmosphere. The sun hits the atmosphere, two things happen. It gets refracted. It bends in toward the moon. So even though the moon should be in the shadow, some light is bending around and getting to it anyway. And as the light goes through the atmosphere, and it's going through the long way, it's not going through straight down, it's going through a lot of atmosphere. The sky is blue because blue light is scattered by the atmosphere. When you go through the atmosphere the long way, a lot of blue gets scattered. And what remains is down toward the red end. If you took white light and took away blue, you'd get a reddish brown. So that's why it's that color. That's light that skirted the Earth, got refracted by the atmosphere to hit the moon anyway, but it hit it without blue. That's a lunar eclipse. They're frequent. Even in Ohio, you can count on seeing one. Maybe not this year, but next or the next, because they happen all the time. Or if you want to work at it, you can zoom in, increase your focal length, and get some details. You can get down and look into the Theophilus crater or any other thing that's on the side towards us. You won't see any flags or rover tracks, but you'll see craters. And the moon has phases, of course, not because it goes into Earth's shadow. That's a lunar eclipse. But because the moon is being illuminated by the sun, and we're looking at the moon not necessarily straight on. If the sun is directly behind us lighting up the moon, we're going to see the whole moon lit up because it's facing, we're looking at the side that's facing the sun. That's a full moon. But as it here, the sun's way off to this side somewhere. And it's lighting up this side of the moon, but oriented away from us. So most of the moon is not being illuminated. We're looking at the dark side here, and then just the little bit that's being illuminated. So we can observe the moon's phases, and that's interesting. We can see Mars. We can image Mars. If you live somewhere with amazingly good seeing, you can get some astonishingly good images of Mars. If you're in Ohio, especially if you're in the heart of a city, you get like this. That's what you hope for. Greater detail is not available because of the disturbances in the atmosphere. Jupiter's a lot bigger, so it's arguably an easier target. Also, it's a higher contrast target than Mars. But again, you can't get that super high resolution that the real serious images get. The atmosphere is always in the way. This is Jupiter's largest moon, Io. There are 4 Galilean moons. We call them that because they are the 4 moons that Galileo observed with his primitive instrument. I eat green cheese, and I always get in trouble on this one. I is for Io, and Io is for Europa, thank you. G is for Ganymede, and C is for Callisto. I can always get 3, but I usually can't get 4. Because I don't do this frequently enough, I guess. So we can see the 4 Galilean moons, and we can also see all the other ones. But if we exposed it, if we lengthened our exposure to bring out the other moons, the planet would be completely burned out. So we usually settle for just the Galilean moons, if there happen to be any in the field at the time. Half the time they're behind it.
What about burned out?
It'd be
Well,
overexposed.
Yeah, thank you. That's a better word. It would be it would just be solid white. It would be saturated. Uranus. You can see that it's a planet. You can see that it's a disk anyway. And it's 2 major moons, Oberon and Titania. And obviously it's not a star. Plus it's got some color to it. It's vaguely blue-green. So you can shoot Uranus and know that you're shooting Uranus. You could shoot Neptune and know that you're shooting Neptune. Again, it's got a disk to it. And we can see Triton, its primary moon. And it's got some color to it, little blue, little green. However, we go past farther out than that, and we get to our dwarf planet Pluto. Well, Pluto, that's a picture of Pluto right there. It just looks like a star. It's not real bright, it doesn't show a disk. And the only reason I know that's Pluto is that I took a frame that I knew contained Pluto on that date, and then a week later, I shot the same area, the same region of sky. You can see, the stars are same generally. But this star isn't there in this frame. And this star that wasn't there in this frame is. Therefore, I know that had to be Pluto. Nothing else would have moved relative to the background stars. So that's how you prove you got Pluto. You just have to look at it a week apart and either have a picture or a very good memory. And we can see asteroids. And again, it shows a visible disk. No color, but you can see the disk. You know it's not a star. And I just happened to catch it in the same field as an open cluster, M101. So I grabbed that shot. And comets. This is 17P Holmes, which I took in, must have been 2017. Huh? And it's not a great image. Trouble with shooting comets is it's moving relative to the background stars. If you shoot with a long enough exposure to get a decent image of the comet, you've got all these stars trailing in the background, moving relative to it. If you track on the stars and make them nice sharp points, then the comet smears. So 2 ways to handle that. The right way is to take a shot of the background stars and then crank up the exposure time and take a shot of the comet and blend the images, after first subtracting the stars from the comet image. I got half of that done. I took the comet image and I got rid of all the background stars because they were all smeared. But I never bothered to take the other frame to combine with it. So all we have is a comet, as though there were no background stars, although obviously there were. Celestial objects, which is everything else, everything outside the solar system. And again, long, long list. But we can blow past that quite quickly. We can shoot novas. Nova Delphinus, 2013. About 13,000 light years away in the constellation Delphinus. And I managed to get an image of it. If you look at an earlier picture of that same field, there's nothing there. And now suddenly there's the light of, oh geez, a lot of light. That's what happens in a nova.
How long did that take for that to appear? I mean, fully like that, from nothing to that?
Weeks, days. Process is fast. What happens is, generally a nova, and we'll talk about this more when we get to the nebulae. Our sun is stable. It's been running for 4.5 billion years the way it's running today. It's doing hydrogen fusion. All the hydrogen atoms coalesced into a star. There's a lot of it, so there's a lot of gravity. The hydrogen atoms are being pulled toward the center very, very, very powerfully by gravity. However, the pressure in the center is so much from all this gravity, from all these atoms trying to approach the center, they've actually achieved the heat of fusion, and they're fusing into helium atoms. So everything on Earth is powered by fusion in the sun, one way or another. And it's always hydrogen being converted into helium. What happens is eventually, and it won't happen to our sun for another 4.5 billion years, but eventually a star, it just runs out of hydrogen. It's been making helium all this time, and the helium's been migrating out toward the surface, but some of it stays there, and it kind of poisons the reaction. So between the helium interfering with the hydrogen fusion and less hydrogen being available, at some point that flame is going to go out. It's going to stop fusing hydrogen. What's going to happen then is all this helium that's been floating around all this time, it's going to start coming in toward the center because there's nothing in the center driving it back out. It's the energy from that fusion that is in stasis in relation to the mass bringing the atoms in. It's balanced. There's so much energy pointed out because of the fusion and so much mass pointed in because of gravity, and it's stable. But when the flame goes out, when it stops using hydrogen, the helium all collapses in because there's nothing opposing it now. It'll collapse in, and when there's enough of it, it'll start fusing helium, which is a higher energy level completely. When that happens, the sudden force outward in this higher energy than helium fusion, it's going to actually blow off a huge amount of the mass. That mass is going to leave. It's going to be heading out to outer space. And after that energetic event happens, whatever didn't get blown out into space is going to fall back in again and create what's called a white dwarf. It's going to fire a fusion again, but there's much less mass now. It's going to be much less energetic. A white dwarf can last a really, really long time. The less energetic a star is, the longer it can last. So you've got this stable white dwarf. It was the process of the blow up is what you're seeing here. And we know that a matter of weeks from then, it was down to a white dwarf. The mass had gone far enough away from it that it wasn't glowing at all. So novas happen pretty fast when they happen. Of course, it happened 13,000 years ago, before we found out about it. Open clusters. One of the easiest ones to see and recognize is the Pleiades, or the Seven Sisters, or Subaru, the Japanese call it, which is why the Japanese Subaru automobile uses that as their logo, or Messier 45. It actually is an open cluster, but we can see some nebulosity. What's this glow here? These stars are young, and they're very blue and very bright and very hot. And they were formed not so long ago. That the gas that coalesced to form them, you know, some of it remains. It didn't all coalesce. They were in the middle of a field of this stuff. So now the stars are lit, and the light from those stars is lighting up all this diffuse gas and dust and junk. And that's why we see it. It's like the moon, it doesn't generate light. It's being illuminated by a nearby sun. Another open cluster. Open clusters are characteristically, they're combined, normally they're made of different stars, different ages of stars. They just happen to be in the same region, and they're gravitationally linked. But they're not all the same age or the same color or the same brightness or the same size. And the more variety you have in age and size and color, the prettier they are. That's why this double cluster, NGC 869 and 884, is a real attractive object, and one that we frequently try to show the public because it's just so darn pretty. We get a nice variety of colors and brightnesses. Nice looking open. Some of the opens are really pretty. This open is not all that pretty. It's M46. It's pretty generic, I think. But look at this. What's this blue thing? That's a planetary nebula. It just happens to be in the same direction. Not associated with it. But if you take an image of M46, you're going to catch that planetary. And that makes for interesting contrast, and I think a good image. M44, people seem to like it a lot. It does have some contrast in color and brightness. I just think they're prettier if they're a little more dense. Like this. That's a nice dense cluster in Puppis. Nice grouping of colors and brightnesses, nice contrast, I like it. But there are also globular star clusters. Globulars are different. Globulars all formed at about the same time. All the stars in a glob are about the same age. All the stars in a glob are about the same size. All the stars in a glob are about the same temperature, which means they're about the same color. And scientists love that. If they're trying to study a star, they have to get a spectrum from it. And there has to be a certain brightness for it to be enough light to get a spectrum out of. But a glob, all the stars are the same. We only have to get enough light from the whole cluster. And we can analyze it. We can pull a spectrum, because we know we're looking at the spectrum of each star within the glob. So we can study the spectra of stars much farther away if they're in globs. Also, if you went back to that original image, which I'm not going to do, we talked about the galaxy being wide and flat, and most of the matter is within that narrow range. Globs are different. Globs are above or below the main concentration of matter, the main concentration of stars. That's why they're still globs. They're isolated. Nothing interferes with them. If they were in the mainstream mixing it up with all the other stars, they'd dissipate. They wouldn't last. So the globs we see are the globs that remain, and that's the globs that formed out where they're on their own and relatively protected. They all kind of look similar to each other. M13 is just pretty. You don't have any contrast in color and size because they're all the same. But you get to see how deep into the core you can see. I like globs. I like to shoot globs. M15 is another pretty one. M5 is another real pretty one. It's a lot smaller and dimmer. But if you crank up the aperture and the magnification, it's at least as pretty as M13. Galaxies now. We talked about spiral galaxies. They're all going to be spirals. Almost so. And you can see the spiral arms. This is M33, a relatively close one. It's in triangulum. It's relatively diffuse because we're too close to it. And it's a challenging target to image, but if you get it, it looks kind of like that. 101, Whirlpool Galaxy, I think. There's a major, again, we see the spiral arms. And we see some star-birthing regions in the outer arms. That's what that is, that's what that is, that's what that is. And we see the core. But we might be looking at a galaxy instead, edge on. Here we go. NGC 5907 in Draco. And again, if this were our galaxy, the globs would be outside the primary part of it. And if it's got globs, that's where they are. Remember, every galaxy is billions of stars, even the relatively small ones. And I'm not counting the greater and lesser Magellanic Clouds, because they aren't exactly galaxies anymore. And they don't have billions of stars, but they're not galaxies.
What are they?
We'll get there.
Okay.
We'll get there. Another pretty much edge-on galaxy, Pegasus. My prettiest galaxy, I prefer M63. I think it's the nicest looking galaxy of all. Pretty much edge-on. M51 is wonderful for outreach because it's so bright and it's large enough that it's easy to see. Doesn't take a huge amount of magnification. You get nice details in the dust lanes. You get some star-breathing regions, little hydrogen alpha activity there and there. Lots of detail. I just don't think it's quite as pretty as M63, but it's certainly easier to look at. And again, wonderful outreach. If Benetachi is up, you're going to want to show people M51. I've seen M51 in a big telescope, a 30-incher, and visually there was a great deal more detail than you get in this image. You can see right down into it. That was quite an experience. Here's a galaxy that's not a spiral galaxy. Why isn't it? It's the Whale Galaxy. It's distorted. ARP, A-R-P, published a catalog, ARP's Peculiar Galaxies. And he listed all the galaxies that were goofed up. It had to be formed as a spiral. The fact that it's now a degenerate galaxy means it ran into something. It mixed with another galaxy. It got distorted. Now the hockey stick down here, same kind of thing. It's not a spiral. But it had to be at one time. Whatever goofed the whale up probably goofed up the hockey stick. They're distorted. They're degenerate galaxies. M81, almost face on. Get some nice details in the dust lanes. M31. Somebody asked what orientation M31 was to us. Well, you look at how oval it is, and you think, well, probably 40 degrees. It's not face on, but it's not edge on. It's somewhere in between. Maybe 40 degrees or so. And that galaxy is also that way, but that galaxy is pretty much face on. So it's just, it's just luck. Leo Trio, we've all looked at the Leo Trio. We've all used it as an outreach object. You get the Hamburger Galaxy, NGC 3628, and 66 and 65. None of them are face on. If you really zoomed in on the Hamburger Galaxy, you'd see why I call it that. Looks like one to me. Nebulae is what we have fun looking at. Make sure we're good for time. Yeah, we are. Nebulae tend to be the prettiest, the most colorful, the most interesting things that we can look at. And the public loves them if we're smart enough to pick the bright ones, which we are. Oh, and the Magellanic Clouds are so degenerate. There's almost nothing left of them. They're more like a cluster that blew up. There's not nearly enough stars to make a galaxy anymore. But they must have been galaxies. And they must have been, well, I think in that first chart that I showed, I think they're shown as within our galaxy, which kind of tells you what happened to them. They got interfered with by us, and they had the bad luck to take all the damage, and ours didn't take damage. So now they're part of us in a grossly deteriorated, distorted way. Very pretty if you're far enough south. when I go far enough south, the skies are never any good. It's just like being at home, you know. I've never really seen them. I get down there as much as I can, but it's never clear.
Cells are rare.
When I do the voyages, we always try to do a stargazing session because the passengers really want to, and they've been told quite accurately that the sky is darker than anywhere else they're ever likely to be in their lives. It's true. The sky above the ocean's dark. Sadly, the ship is not. You got lights shining on you. You have to worry about letting it goof up your night vision. But more importantly, you're under the marine layer. There's always moisture coming off the ocean. You're looking through that. So it tends to be real hazy. We get occasional good, clear, super nights, and they're among the most enjoying stargazing experiences I've ever had. But we don't get them every trip. We don't get them every other trip. We don't get them very often. But we always try. Passengers love it when it happens. They tend to blame me when it doesn't. I don't know. I don't control it. I don't
Is it
control
still
any of it.
typically better than at the observatory here?
No, that marine layer is worse than you
Is it?
think. If you're looking up through haze. But when it's good, it's way better.
Yeah.
Way, way better. But not that frequently. A dark nebula is, we have to kind of infer it. We're looking at something and then we notice that some of it's being blocked. There's something in the way. And what's in the way is this dark nebula. In this case, the head of a seahorse. This nebula is near Orion's belt. It's a big reflection nebula. I think it's reflection. You're not seeing any detail because it is a reflection, I think. It's just a big red nebula. But we notice this with nice sharp edges. And notice also we're not seeing any stars in that region. Where if that were an opening in the nebula, we'd see background stars better, not worse. So that's just something that's closer to us. It's in between, it's in the way, and that's what a dark nebula is. Just a cloud of dust and gas and junk. And we only see them when they interfere with our view of something. The Cocoon Nebula, it's got this chunk out of it here. That's a dark nebula. In fact, it's kind of surrounded by a dark nebula. Notice that there's fewer stars in this region. That's because the dark nebula is eating the stars too. The Cocoon Nebula would be much brighter, and it wouldn't have all these patches in it if we could see it properly without junk in the way. And again, the Pac-Man Nebula, same kind of thing. There's a chunk missing, and it's because there's a dark nebula somewhere between us and it. But the pay dirt is the emission nebula, and the reflection nebula to a lesser estate, but primarily the emission nebula. We really care about them because they look so striking. Look at this bubble nebula, M52. It looks like a bubble. It looks like a soap bubble. It's also called a planetary nebula. I described how a star can fail, go nova. It blows off all this matter, and then what remains that didn't go fast enough to escape collapses back down and it turns into a white dwarf. Well, that's what happened here. This is the dust and gas and junk still trying to escape from that central event, moving as fast as it can in all directions, which is why the wavefront appears to be a sphere. And it's being excited by that white dwarf that's still in the middle. It's an emission nebula because what we're seeing is hydrogen atoms that are being excited by ultraviolet photons leaving that white dwarf. Those photons are striking the hydrogen atoms and disturbing their electron shells. They're driving their electrons out to a higher energy shell than where they belong. That's not the natural state. When that happens, it inevitably has to collapse back down to where it does belong. When it does this, it always has to emit a photon to get rid of that energy. Energy is preserved. And it's always going to be the same energy. It's quantum. Things are in quanta, in specific quantities. Hydrogen alpha photon is always going to be the same energy. The amount of energy it took to drive it out of its electron layer, that it recovered falling back down to the normal electron layer. Specific amount of energy. The energy of a photon determines its wavelength, which is also its frequency, which is also its color. So the energy of a photon tells you what color it is. Well, hydrogen alpha photons are bright, dark red, blood red, deep red. That's why it appears that color. Come on. The reflection nebula should not be so red. Just a little bit of careless processing on my part. The reflection nebula instead is just dust and cloud and gas and junk that's being illuminated by a nearby star, as I just said a little bit ago. And we already used this as an example of a dark nebula. Again, notice the nearby stars are kind of gone. What that is, it's probably an emission nebula. It's probably the other kind, not a planetary, not caused by a failing star. Star birthing regions where stars are forming. There's a lot of hydrogen floating around. Am I moving too far away again?
Oh, yeah.
There's a lot of hydrogen moving around and compressing and forming stars. But after it forms stars, what didn't go into the star is still hanging out there. So new stars are generally surrounded by unassociated hydrogen atoms. So these are called H2 regions. It's regions where there's a lot of hydrogen surrounding a lot of recently birthed stars. And what happens is the energy from the star strikes all this hydrogen that shouldn't really be that close to a star, but is, and does the same thing. It drives the electrons out one shell, the electrons go down, and you get your hydrogen alpha photon in the red. I believe that, well, it's wrong in the first place. They call this a Pelican Nebula, but it's perfectly obvious to me that it's the pterodactyl nebula. They just name it incorrectly. And I believe that's the other kind of emission nebula. Again, it's star birthing. There's a lot of new stars being born, but there's a lot of hydrogen hanging around from when they were born, and it's being excited and emitting hydrogen alpha. Or the jellyfish nebula, which is cool. I think it's attractive. And again, it's not a planetary emission nebula. It's the other kind of emission nebula from an H2 region. Newly birthed stars surrounded by debris. Crab Nebula is surely a planetary. We know that in 1060 something, 1050 something, 54. Pardon? 1054. Thank you, 1054. See, I don't have to know all this stuff because I got you guys.
Yeah, Ron.
We know that the Chinese and Japanese astronomers noticed the star that didn't belong. I mean, these people looked at the sky every night, and they had clear skies back then. They didn't have light pollution. They knew what the sky looked like. If a new star showed up, they knew it. It was obvious to them. That's why they called it a nova. A new star that didn't belong. That's because the star had collapsed and then blown off all this matter when it went into helium burning. And again, here we've got all this mass in the process of leaving. Now, we've been talking about hydrogen alpha because hydrogen is the most common element out there. And the hydrogen alpha photon is relatively low energy. The red is at the low end of the, as far as energy is concerned, of the spectrum. The high energy end of the spectrum is blue, indigo, violet. So red is relatively, the hydrogen alpha is relatively low energy. But, you know, there's helium there too. Because when the star blew up, it blew off a lot of helium that had been forming within the star forever. Helium is going to light up green. It's a higher energy photon. When you take a helium atom and drive an electron out one shell and then it collapses back, it's going to emit a green photon. Oxygen is going to emit a blue-green, teal photon. I took this image of the crab using a hydrogen alpha filter and an oxygen 3 filter. So I didn't see hydrogen, though I know it's there. But I see the O3. I know there's a lot of oxygen in that region. And the reason why, and you will always in a planetary nebula, you'll always see oxygen toward the center and the hydrogen toward the outside. It's not really that that's the mixture that's there so much as right in close to this white dwarf, you've got the most energy and you're creating the most energetic reactions and you're able to drive the oxygen up. Farther out, you don't have enough energy. You're not getting hit with enough photons. So the oxygen isn't getting switched, but the hydrogen is, so we just get the red. It's just, it's not really a good judge of where the property is. M42, combination. Here in the bat wings, the core, that's pretty obviously a star-birthing region. So it's an emission nebula from star-birthing. Then out here, that is probably not emission, that's probably reflection. And of course you got the Running Man up here and whatever it's called down here. Again, at outreach events, we're always going to show them M42 if it's available. Heck, it's a naked eye object. You can tell it's there, you can smell it. With binoculars, you can see it reasonably well. It's just an obvious outreach item. I rely on it when I get lucky and have a stargazing session on the boats. Because for one thing, they can find it. Orion is by far the easiest constellation to recognize. It consists of 7 unusually bright stars. When you're looking through haze, you might not see anything, but you'll see Orion. It can punch through that haze. So yeah, we rely on Orion when it's that time of year, which it just now is not. But it will be again. Another interesting one, NGC 60 and 88, the Crescent Nebula. Again, she wants a detail. I'm going to go back a minute. Look at this. It's dynamic. I mean, it's not. If you look at it 2 years from now, it's going to look the same. It's not moving fast enough. But look how royal the material is. It's tremendously disruptive, which is what makes it interesting to look at. And in the Crescent, we get the same thing. We see a lot of detail, lots of things changing. And in context, here's the Crescent again. And again, we can see a lot of detail. There's stuff happening. Trifid Nebula. It's got some red and it's got some blue. That makes it kind of interesting. It's reasonably easy to see if you're using narrowband filters. It's an okay outreach object. People don't recognize, they don't call them planetary nebulae sometimes. The planetaries that I've shown you so far, but we always call M27 a planetary. But it has the characteristics that we're always going to see in planetaries. Again, it's a star blew up. This is all the matter that's leaving the star, being heavily excited by energy from the white dwarf that happened when the material collapsed back in. And again, we see the high energy oxygen stuff in the center and the lower energy hydrogen stuff on the outside. That's characteristic of a planetary. They're called planetaries because when the ancients first saw them, they didn't have a whole lot of categories for what they saw. They knew what a star looked like, so they were pretty sure of what was stars. And there were these fuzzy things, and they called them nebulae, which kind of means cloud or something. It just means fuzzy. And then there were planets, which were large enough to show a disk. They didn't know what they were, but the word planet is what they used. I think it meant wanderer. They had a disk and they wandered. So they called them wanderers or planets. And then there were these things that were fuzzy, but had a round shape to them. So they called them planetary nebulae. And that's why we still call them planetary nebulae. It had nothing to do with the planet. It's just what we call them. And again, another shot. Again, we've got all the excited oxygen in the center. And at the outer edge, only the hydrogens get lit up. Same with M57. And you can even see a star dead center in it. That might be a coincidence. Or it might be what's left of the white dwarf that's driving it. No easy way to tell from here. And of course the helix. It's a terrible picture, but it's the only one I've ever managed to get of it. I wanted a shot of it. The helix never rises above the trees for me. So I shot that through trees. Yeah, I got what I could get. It's like people don't applaud a dancing bear because he dances well. Just that he dances. So here I got an image of that's my dancing bear image. And that's what I've got. So are there further questions? You're very, very kind. Thank you.
How big a telescope were you using on most of those?
7 to 12 inches, mostly. I've had a couple of 14 inchers, but they happen to be during low activity periods for me. So I didn't get a lot of images with them. Actually, the same for the 12. Most of my high activity periods were using something between 7 and 10 inches.
So, Ron, that would mean most of the stuff we saw there in the miraculous sky could be seen from the observatory.
Could I answer that one?
John lives in Wadsworth, so
Pretty much everything I could image in Wadsworth, you'll be able to smell from the club's observatory in a 16-inch. But bear in mind, I'm imaging. I can see so much deeper imaging than I can visually. But you have a much darker sight than I have. I know we talk about the good old days when it was certainly better. But today it's still a whole lot better than my place. And you have a bigger telescope. So yeah, they're not going to look like this necessarily, or probably. But you'll see them, you'll smell them. Just don't, I always recommend not subjecting the public to what we call the faint fuzzies, because they don't really appreciate it and they don't know what they're looking at. We're thrilled that we can detect it. Wow, look at that, I can smell it, it's there. We're impressed by that. The public isn't. The public wants to be smacked in the face with Saturn or M51 or something obvious. Yes?
You took all those photos, correct?
Yes.
Okay, now, the photos, there's lots of lights, which are stars, or galaxy stuff. Are they light years apart, even though they look close together?
Yes.
And if
Most
they're
of the
light
time, they
years-
just happen to be in the same direction.
But they could be further away or deeper
Yeah,
out.
yeah. The constellations are a good example of that. Sometimes on TV shows, they'll talk about a constellation as though it's a location. The constellations aren't locations; they're merely directions. Because the stars that make up the constellation, they're in the same direction, but some are 100 times farther
Different
away than
distances,
others.
right?
We just see them in this grouping. The only things that are actually associated with each other are open clusters are associated. Those are in the same region. Globular cluster, by definition, are in the same location. Anything else? Double stars, there's what we call visual doubles and double stars. Double stars are actually double stars, two-star system. A lot of the time there's a star that has another star right up next to it, visually.
It could be.
Yeah, it has nothing to do with it. but it looks like a double. So we have to distinguish between direction and location.
Is it okay to say that even though they're 100 million light years away, they may not be there now?
Oh, yeah.
Whatever
yeah.
we're looking at.
Yeah, yeah, stars end eventually. Generally not within 100 million years, but the big telescopes, the space telescopes, Webb, I think, is looking like 15 billion years out. So yeah, a lot of that stuff's probably gone.
We haven't reached the end of the universe yet, have we?
And we haven't reached the end. We go deeper every time we improve our system. But there's a limit to how deep we can get, because there's junk in the way. There's always something closer.
I have another question.
Yeah, go ahead.
Could you explain the phases of the moon? I always thought that there was an eclipse every month because the new moon was dark and the Earth
Oh,
got
okay.
away. You know, that's not true.
Yeah, that's not what an eclipse is. Can I steal this chair? And I'm gonna steal some water.
You can keep it.
I'm supposed to have an orange and an apple to give this talk. But what it is we know the moon is tidally locked with the Earth. As the moon rotates around the Earth, it always has one face toward the Earth. So it rotates at just the right speed to compensate. We know that we only see the moon because the sun shines on it. And if the sun were directly, perfectly in line behind the Earth, it would be an eclipse every month. But it isn't.
But somehow the Earth's shadow gets in the way. Or
Yeah.
the Earth's shadow gets in the way of the moon.
That's
why we
an
have the
eclipse.
phases.
No.
But it's not a phase.
Okay, phase is what I'm after.
Okay. I'm gonna take a drink of the sun here. Okay, Earth. Moon. I'm the sun. Okay, so we get the moon here between us and the sun. Well, the side that's facing us is dark. We can't see it. It's not dark because it's black. Oh,
Here's the moon.
here we go. Now we got an orange. Here's the moon. So I'm lighting up this side of the moon where nobody can see it because there's nobody over here. People on Earth can't see the moon because they're looking at the dark side. If you had a really big flashlight, you could see the moon. It's there. It's just not being illuminated. That's a new moon. We get over here. I'm lighting up this half of the moon. We're looking at this half of the moon. So a substantial part of the moon, the portion of the moon that we can see, is being illuminated, but a substantial portion of it is not. So we've only got this much of the moon illuminated. That's the crescent moon. That's what it goes through every month. It waxes toward full and then it wanes toward the new because the moon keeps moving. Now at this point, I'm lighting up this half of the moon. We're looking at that half. We can see exactly half of the visible portion of the moon is lit and half is not. We could see it if it were lit, it just isn't lit. There's nothing blocking anything, but the sun's over here and can't light up this side. So that's the phases. Then we get here. If everything lines up really, really perfectly, we got an eclipse. The moon is an Earth's shadow. And then we come back out. But if it isn't in the shadow, then that's a full moon. We're looking at the side of the moon that's being illuminated. Because it's up here, we're down there. Things aren't in perfect alignment. So if it's up here, we're going to see the side that's illuminated without the Earth interfering at all because it's not perfectly lined up. But the lunar eclipses do happen with fair frequency. Cause they're pretty close to lined up and the wobble's not that great. But yeah, that's my attempt at an apple and orange description of the moon phases.
Thank you.
And obviously I should have a screen. See, I'm not used to astronomers. I talk to people that just showed up because they need something to do on a sea day. They're not really, they didn't know they were interested in astronomy until they walked in. So I don't get the same kind of questions. That's a cool question. I'm gonna change my talk. I'm gonna include a slide or two about that. So I don't feel quite so helpless trying to describe it in case anybody does ask.
No charge.
I saw in one of my astronomy classes in college back when I had dark hair. He had a great big bright light right there at his podium, and he had one of the students with a beach ball, and the students circumnavigated that bright light.
Oh yeah, that would do it.
And it was so cool, and then you can see all the lights going off in people's brains, and obviously when the ball is on this side of the light's behind it, it's dark, you don't see anything. And as she went around with that beach ball, then you started getting the phases of the moon. And that made it crystal clear for everybody. I thought that was the coolest demonstration of that. But you gotta have a big, obviously.
It's a very good
big
illustration,
space.
I agree.
Oh, it's cool, it was cool.
All he has is apples and oranges.
Yeah, you guys apples and oranges. She had a beach ball.
Are there more?
Just a comment from something you mentioned, because I've lived in Australia a while. There's a lot of really clear sky in Australia. Even outer suburban areas are just magnificent.
Oh yeah, desert's wonderful.
Because you get out in areas of lower humidity and even areas that have some humidity. It's just the nature of the atmosphere there and the dust and everything else, I guess.
Oh yeah, dry air is wonderful, wonderful. That's why we have so many observatories in our deserts,
Yeah.
and
But
yeah, it makes a big
way out in
difference.
the middle of nowhere in Australia, you see a lot more than you can see around here. I know
Yeah, I know people that have gone there for star parties and just can't wait to go back.
when we moved back here, we lived just a couple miles from Lake Erie, and I was shocked at how little you could see. You can't see it.
Come by my place, you won't see much. The downside is I've never managed to book an Australian cruise. Because, well, A, they're too cheap to transport me there. And B, they really want destination speakers. They want experts on New Zealand and New Caledonia. I do, in Richmond, I talk science. And there's different, there are naturists that go on these cruises, and there are destination speakers that go on these cruises. And then there are enrichment speakers like me. But the cruises I like best don't tend to want people like me. They want naturists, and they want the destination speakers. So I've only ever managed to snag one Alaskan voyage for a speaking gig, and I've never managed to snag Australia.
One of my favorite sky objects, because in 7th grade, we'd done a project, the whole class, on our trip to Alpha Centauri, the closest star to Earth. And it was so neat getting there because you actually see it from Australia. And of course, it's very, very bright.
Yeah, plus there's cool stuff near it.
Yeah, it points to the southern
There's that
cross.
one degenerate galaxy, what's it called?
It's one of the points.
The
of the
larger
Southern
and
Cross.
smaller Magellanic Clouds are viewable.
Well, they're in that direction. But there's a galaxy, it's got a big line through it. That somebody help me out here because I can't remember what it's called. Bummer. I actually managed to see it once from the far end of the Florida Keys. It just didn't get up very high, but it got up high enough I could see it. I think I even grabbed an image of it. Centaurus X. It's been talk about when my hair wasn't white. That was a while back too. But I know the club officers are going to get impatient with me because we're late getting on to the business part of the meeting. But thanks very much for your attention and your questions, and You've improved my presentation, so thank you for that.
No charge.
John, are you still imaging?
It's been a few years. I never got started back up again after COVID. Everything's in there. I just haven't physically made it up the stairs.
Are you still going on those cruises you're talking about, or?
Yeah, I'm doing that as much as I possibly can. I've done 3 this year, and I got 3 more coming this year.
Wow.
And I've got, I think, 5 booked for next year so far.
They're paying you to speak?
Well, we're not allowed to talk about that.
Oh.
Need someone to carry your luggage?
But there's a reason I'm going.
Yeah.
Thank you, John.
Thank you.